Okay, chapter 7 is on systems of equations and inequalities. So section 7.1 and 7.2 are dealing with not just linear system, but two variable systems, which you will remember from Algebra 2 and Algebra 1. So for example 1, it's mostly just to remind you of some of the terminology and scenarios of linear systems. Okay, so scenario 1 would be, let me see, I have a line going like this, another line going like this. Okay, there's exactly one solution. The solution lies right here. Okay, the solution is written as an ordered pair. Okay, so if I asked you to solve the system, you would write the ordered pair. If I were to characterize this system, this is called a consistent system because it has a solution, so it makes sense. The two equations go with each other. Okay, scenario 2. Let's draw two parallel lines. Okay, this is also a linear system. There's two lines. If I were to solve this system, there's no solution because they have no points in common or no points that satisfy both equations. If I were to characterize this system, this is an inconsistent system because there's no solution. So it doesn't really make sense that those two lines would go together. Okay, the third scenario. Here's one line. Okay, now the second line is actually going to be right on top of the first line. Okay, in this case, they have many points in common. In fact, they have infinite solutions on the line. So I might say there's infinite solutions on 2x plus 5 equals 10 or something like that. 2x plus 5y equals 10, I should say. Okay, what is this? This is considered a consistent system because there's a solution. There's actually many solutions. Okay, these are dependent. If I were to list the solutions, the y value depends on the x value, whereas on the first scenario, there was exactly one solution. So the x and y were completely well defined. Okay, now we're gonna go over what some special systems look like algebraically, and you'll remember these. Okay, so I'm gonna go ahead and solve the first one. The first a, 2x minus 3y equals 5 and negative 2x plus 3y equals 7 looks set up for elimination. So I'm gonna go ahead and use elimination. If I were to use elimination, let's see, cancels. So I'm left with 0 equals 5 plus 7 is 12. Okay, now because 0 is not equal to 12, this is an inconsistent system. So when I solve it, I would say there's no solution. Okay, and the proof that there's no solution is this false statement here. So make sure you write down the false statement, which is, in my case, at 0 can't equal to 12. It could be a different false statement, but it still leads to no solution. And of course, if you're writing out no solutions a lot of trouble, you could always do the 0 with a slash, which means empty set, which means there are no solutions in the solution set. Okay, B is also going to be a special system. However, given the way it is set up with that y equals negative 2x plus 5, I'm going to use substitution because that seems to be the best start to this. So where the y is, I'm going to go ahead and substitute the expression negative 2x plus 5 equals 10, and then I'm going to solve it. 4x minus 4x plus 10 equals 10. 4x minus 4x is nothing, so I end up with 10 equals 10. 10 equals 10 is a true statement. So this is a consistent system, but the 10 equals 10 tells me that there's actually infinite solutions. Okay, and in the past, you would probably leave it at infinite solutions, but now we're going to write the answer in terms of parameter A. Okay, I could also say there's infinite solutions. It's all the points that lie on 4x plus 2y equals 10 or something like that. Okay, in this chapter, they're going to ask you to use parameter A, so I'm going to introduce that here. So if they say in terms of parameter A, okay, I have to either let x equal A or y equal A. It doesn't matter which one, but sometimes one of them's easier. Okay, because I'm going to have to solve for the other variable, I want to plug A in the easiest spot. So I'm actually going to let x equals A. Once you see it, you'll understand it a little bit. You do need to tell me whether you've let x equal A or y equal A so that it will make sense to me and I'll know what you did. Okay, if I let x equal A, I'm going to plug a in for x. I could do it in either equation. I could do it here, or I could do it here. Since this one's already solved, I'm going to go ahead and plug it into that equation. So y equals negative 2a plus 5. I plugged x equals a in. Okay, if I was going to write my answer in terms of parameter a, then the x coordinate is a, my y coordinate is negative 2a plus 5. Okay, and since there's infinite solutions, if I followed this pattern where I'm plugging in a real number for a, it would give me all the possible ordered pairs that satisfy this system. Okay, now for example 3, I'm not actually going to solve these. I'm just going to show the first step to give you some suggestions for strategies if you get to a question like this. Okay, so for example A, it looks like elimination. I would use elimination, especially with no calculator. But with no calculator, I don't want to have to deal with the decimal, that's for sure. Okay, so on the first equation, I'm going to multiply by something that would cancel out the decimals. So at least I don't have to deal with decimals. If you love decimals, go ahead and use them. Okay, I have 0.8x plus 2.3y equals 4. So to cancel the 8/10 and the 3/10, I'm going to multiply everything by 10. Okay, if I do that, I'm going to put it down here. I would get 8x plus 23y equals 40. Okay, I still have to solve it, but at least there's no more decimals in it. Okay, and then for the second equation, the same. If I don't want the decimals there, I want to multiply by a factor that will cancel out the decimals. So I have 0.12x plus 0.14y equals 3. So that's 12/100ths x plus 14/100ths y. So I'm going to go ahead and multiply by 100. Then I can rewrite this as 12x plus 14y equals 300. And then from there I could solve it. Looking at it, I would probably use elimination, but it's up to you. Okay, now example B is just showing you if you have fractions that don't have common denominators, you might want to cancel the fractions by multiplying by the common denominator. So for this first equation, 1/2 x plus 1/5 y equals 6. The common denominator between 2 and 5 is 10. So if I multiply the entire equation by 10, it would get rid of eliminate the fractions for me, but it would still be an equivalent equation. So half of 10 makes it 5x. Fifth of 10 is 2y equals 60. And then for the second equation, let's see, x over 3 minus 4y equals 7/3. I'll multiply everything by 3. And I get x minus 12y equals 21. Okay, and then from here you could choose to solve this. You might use elimination. Substitution could be good here because of that x. I could add the 12y and then use substitution. Okay, example 4 I am actually going to solve. These are nonlinear systems, meaning they're not both lines. We have not graphed, well, we've graphed some of these. So for example A, that looks like the first equation is actually a parabola and the second equation is a line. So I'm finding the intersection of a parabola and a line, but I'm going to do so algebraically. Okay, and there's more than one way to solve these, depending on if you prefer elimination or a substitution method. I'm going to do one with substitution and one with elimination, and then you can decide which one works best for you. Okay, so I'm going to go ahead and use substitution for this one. If you wanted to use elimination on this though, let me see. If I look at this and this equation, it looks like the y's would be the best thing to cancel. I would probably multiply the second equation by -1, and then I could use elimination to cancel the y's. But I'm going to use substitution here just to show you substitution. Okay, so let me rewrite the second equation. I want to make it either x equals or y equals. It doesn't matter which one, we should get the same answer. I think I'm going to solve for y. So I'm going to add the x to the other side. So this will become positive x minus 2. Okay, then I'm going to go ahead and make the substitution into the first equation. So 3x squared plus y, what's y? I just solved for y. X minus 2 equals 0. Okay, now I solved for y because it looked slightly easier than solving for x. However, it also made it easier on the next step because if I had solved for x here, I would have had to plug it into this spot, and that would have been more work. It would have led to the same answer, but it would have been more work. So you might want to look ahead and say, which method will be easiest for me? in future steps. Okay, let me put this in standard form, and then I am going to factor it. Okay, you can use whichever method you would like to factor it. Some of you are bewildered by my doing it in my head, so I'm going to show you. Because this is 3x squared as the first term, it must be true that this is 3x times x if it is in fact factorable. Okay, because the last term is -2, this and this must multiply to -2, which means I might have 2 times -1, -2 times +1, +2 times -1, or -2 times +1. One of those has to work. If you guess and check, you eventually get it right. So if I were to guess 1 and 2 and figure out the signs later, if I distributed this out, I would get 3x squared, 6x, and 1x. There's no way I'm going to get that. So I'm going to switch them. Let me make this 2 and 1. Okay, let me see. 3x squared, that's 3x and 2x. I could get a negative x here if I make this a -3x and a +2x. Okay, that's what I do in my head. You can do whatever you would like in your head, or not in your head, in your methods. Okay, but I get x equals -2/3 and I get x equals 1. If you had done a different method, you might have gotten the y values first, which is equally fine. Okay, because I have two x values, there's potentially 2 points of intersection, which means I should have 2 ordered pairs for my answers. Okay, so I need to find both ordered pair solutions. So let's go ahead and plug in. Let me plug in the easier one first, because you know that makes life easier. So x equals 1 is easier for me to plug in. Okay, I'm going to go ahead and plug it in this equation because this looks like the easiest equation to plug it into. I could plug it into any of these equations though. I get -1. So the first ordered pair is x equals 1, y equals -1. Okay, let me go ahead and get the second ordered pair because it has a fraction. Y equals, I got -2/3 minus 2, which is -2/3, minus 6/3, which is -8/3. So the second ordered pair where they intersect is -2/3, comma, -8/3. Okay, so there's 2 ordered pairs, which makes sense. It's a parabola and a line. They could intersect at 2 points. They could intersect at 1 point. They could intersect at no points at all. Okay, I'm going to go ahead and move to example B. We have not graphed ellipses yet. Ellipses look like ovals. So for example B, the first equation is actually an ellipse, which looks like an oval. The second equation is a parabola. Once you've graphed it, you'll kind of have an idea. But if I had an ellipse and a parabola, and I want to find where they could intersect, they could intersect at 0 points, 1 point, 2 point, 4 points. Could they do 3? They could do 3. So there's options here. Okay, but really, what am I trying to do? We're doing it algebraically. I'm going to use elimination this time. Okay, I could use substitution if I solved for x here, or I could solve for y squared here and plug it in there. So there's multiple methods every time. Okay, if I use elimination, let me see. Do I want to cancel the x's? No, because this is an x squared and this is an x. So that would make a mess. Do I want to cancel the y squareds? Yes, because they're both y squareds. So I'm going to go ahead and multiply the second equation by 16. And then I'm going to use elimination. So the first equation stayed the same. The second equation I multiplied by 16. So this is a 16x, which is okay. Okay, now this should cancel because I'm trying to use elimination here. Okay, so let's see what cancels. These guys cancel, which is fine. Let me bring down what's left. The 4x squared is left. This is a positive 16x, and I just put them next to each other because they're not like terms, equals 48. Okay, I'm going to go ahead and solve this. I'm going to put it in standard form. I'm going to hope it factors, because if I had to do quadratic formula and then plug it back in, that would be a lot of work. Okay, this actually has a common factor, so I'm going to take out the 4 so that this will be an easier problem to factor. Minus 12. Okay, let's see, to get -12, we're going to use 6 and 2, a +6 and a -2, so it'll add up to +4. Some of you guys ask about this. This 4, since 4 cannot equal to 0, it's irrelevant to the problem. I could also divide it off and then it would be gone. Since there's no variable out there, it doesn't matter to the problem. It just made my life easier. So I got two different x values. I got x equals -6 and x equals +2. Okay, so there's potentially two different x values. I'm going to go ahead and plug the x equals 6 and the x equals -2 into one of the original equations. It doesn't matter which one I plug it into. I think I'm going to use the second one just because it looks like a little bit easier than the first one. Okay, so I'm going to plug x equals -6 in first. So -6 minus y squared, -y squared equals 8. Y squared equals -8. That doesn't work. So actually x equals -6 does not produce a point of intersection because we can't intersect imaginarily, at least not in the land we live in. So 2 minus y squared equals 2. I'm plugging in the second x value, so I get -y squared equals 0. Y squared equals 0. So I get y equals 0. If that had been a different value, it would have been a plus or minus, and I could have gotten 2 points, which means, what is my solution? When I plugged in x is 2, I got y equals 0. So these actually only intersect at exactly 1 point. But potentially this could have been 4 points. If I had gotten a plus or minus answer here and a plus or minus answer here, I would have ended up with 4 values. But this case, 1 value. Okay, the last example is about break-even, equilibrium, which is a common question asked with systems. It's when the money coming in and the money coming out kind of balance out. Okay, so we're going to go through this example. This is an example of how you might do some kind of problem like this. So a small business has an initial investment of $6,000. The unit cost of the product is $23.20 and the selling price is $35.20. How many units must be sold to break even? Okay, we're going to consider this in two ways. Okay, first let's consider the cost. And this is the cost to the business, not the consumer. Because you're the business owner, you're thinking, how much does this cost me? Okay, so the business owner spent $6,000 as an initial investment, and then to make the product, it's $23.20 per unit. Let's call that X. Okay, revenue is the money coming in to the business. So every time the customer buys something, how much money comes into the business? This is not the profit. Okay, so the selling price is $35.20 per unit. So every time they sell it for $35.20. Okay, now what types of questions did they ask? The first one is normally about a break-even situation. Break-even is basically saying, when is your cost equivalent to your revenue? When is the money going out and in equal to each other? Okay, so if I were to solve this, I would set the cost equal to the revenue. Okay, and ask me how many units, so I would go ahead and solve for X. So 6,000 equals, if I subtract 23.20x, I get 12x. So I get 500 units. Okay, so at exactly 500 units, the amount the business is paying and taking in breaks even. There's no profit, but at least they're not losing money. Okay, scenario B says how many units must be sold to make a profit of $1,000. Okay, so how do we figure out the profit? The profit would be the revenue, the money coming in, minus the cost. You want the revenue to be higher than your cost, otherwise you're not making any money. Okay, so let's see. So what am I doing? What's my profit? Okay, my revenue minus my cost, 6,000. And I want it to equal $1,000. Okay, let's solve for the number of units. So 12x equals, let me add the 6,000. I get 7,000. Okay, I'm going to put it in my calculator. And what did I got? I got 583.3 something, something, something. Okay, I'm trying to make $1,000. I can't actually sell 583.3 units. So to make 1,000, I must actually sell 584 units because 583 would be a little bit, would be not quite enough. 584 would give me a little over 1,000.